Always having been intrigued by historical geology, with its eras of hundreds of millions of years, I was interested to know to what extent it could be and has been tested by experiment. It was for this reason that some years ago I renewed my studies on the subject, and in particular on the application of the principles of stratigraphy to obtain a relative chronology from superposition of strata. I started in the 1970s by reading reports from the Geological Society of America on the underwater drilling campaigns of the American ship Glomar Challenger. It was from these reports that I learned about the works of the German geologist Johannes Walter, one of the principal founders of sedimentology. Before going further, let's explain some of the terms involved. Stratification is the general term for layering in rocks. A stratum is a single layer of homogeneous or gradational lithology deposited parallel to the original dip of the formation. It is separated from adjacent strata or cross-strata by surfaces of erosion, non-deposition, or abrupt change in character. The term stratum includes bed and lamination, which carry definite thickness connotations. Strata vary in thickness from less than a millimeter for microstrata or laminae to more than a meter. A stratum often shows evidence of sorting of the particles of which it is composed, with the size decreasing from bottom to top of the stratum. The large particles at the bottom grade up to the small ones at the top. The limit surfaces are separations between the fine particles at the top of one strata and the large ones at the bottom of the strata which covers it. Bedding planes which can separate two strata, and those caused by erosion of sediments. A facies is a series of superposed strata having the same lithological content. For instance, a series of strata all composed of sandstone, or all of clay, or all of limestone, are called a facies. This cliff face has been divided into facies. The sandstone deposit is coloured yellow, the clay deposit blue, and the limestone orange. Each deposit is subdivided into strata. For 2 centuries since stratigraphy was founded, and without formal proof, strata superposed or sitting one on top of the other, and on a larger scale superposed facies, have been considered as successive layers or isochronously deposited sediment. That is to say that the lower one formed first, and then the one above it formed second, and so on. The principles of stratigraphy arose from this belief of strata and facies being successive layers. The term principle, as referred to in stratigraphy, is defined by the Oxford Dictionary as a general or inclusive law exemplified in numerous cases. It was in 1669 that Nicholas Steno, a naturalist from Tuscany, defined the principles of stratigraphy in his book entitled Prodromus. These include the principle of superposition, where in a sequence of strata any stratum is younger than the sequence of strata on which it rests, and is older than the strata that rest upon it. At the time when any given stratum was being formed, all the matter resting upon it was fluid, and therefore at the time when the lower stratum was being formed, none of the upper strata existed. Steno, 1669. The principle of initial horizontality says that strata are deposited horizontally and then deformed to various attitudes later. Strata either perpendicular to the horizon or inclined to the horizon were at one time parallel to the horizon. Steno, 1669. the principle of strata continuity says that strata can be assumed to have continued laterally far from where they presently end. Material forming any stratum were continuous over the surface of the earth unless some other solid bodies stood in the way. Steno, 1669. These three principles of stratigraphy provided the basis upon which geologists at the end of the 18th century and the beginning of the 19th established the geological column. They assumed that sediments had deposited horizontally around the world and that the rate of deposition was the same everywhere for each layer. Furthermore, since the days of geologists James Hutton and Charles Lyell, it was assumed that the rate of erosion and sedimentation in the past was the same as today. In consequence, the age of a stratum was estimated from present-day rates of sediment deposition and from the depth of the stratum in the hypothetical column of sedimentary rock. Hypothetical because all the assumed stages of the column are never found together in any one geological formation. The method used to date the sedimentary rocks from the Cambrian period to the present was, therefore, based upon the principle of superposition. By applying the principle of continuity, the same age could be given to outcrops of what were assumed to be the same facies, whether in South America, South Africa, or Australia. Later, the fossil content of sedimentary formations in different sites was used to show a correspondence of age between the fossils of one site and those of another. This gave rise to a fourth principle of stratigraphy, the principle of paleontological identity. This principle states that two strata with the same paleontological content are the same age. This means that if the fossils in a layer in, say, the Himalayas are the same as those in a layer in the Appalachians, they could be considered as having the same age. As a preliminary to my experiments, I examined the existing data. At the end of the last century, Johannes Walter studied the formation of contemporaneous sedimentary deposits which prograded or developed from the coast towards the open sea. By drilling into the sediments, he observed the same succession of facies from the surface downwards as from the coast towards the sea. A law was formulated of Walter's observations that facies superposed in a deposit area would also be seen to lay side by side. He examined the sediments in the Bay of Naples. By boring vertically downwards through the sediments in the bay, he saw that the facies that lay on top of each other were in the same sequence as those that were lying next to each other horizontally. The sequence of facies that could be seen lying side by side as he went from the coast out to the sea was the same as the sequence of facies that lay on top of each other in a downward direction. He realized that the belief that the facies at the bottom was older than the one on top was wrong. Quite obviously, all the facies he was examining, the one at the top, the one underneath, and the one at the bottom, were still forming. They were forming sideways, so that part of the top facies was the same age as part of the bottom facies. This phenomenon can also be observed during coastal marine floods. In the 1970s and 80s, several holes bored into the bottom of the Pacific Ocean by the vessel Glomar Challenger produced samples of sediment that showed that Walter's discovery of superposed and juxtaposed facies also applied to deep sea. An example from the Grand Canyon is given later. Walter's observations show that facies in sequences superposed and juxtaposed at the same time do not follow the principles of superposition and continuity. This phenomenon, confirmed and explained later on by our experiments in the laboratory, is shown to be a natural consequence of sedimentary mechanics. In 1970, I received a report from the American geologist Edwin McKee of his 1965 observations of sediments deposited as a result of a river in Colorado overflowing its banks at Bijou Creek due to 48 hours of torrential rain upriver. The stratified deposits, reaching a thickness of 12 feet, exhibited particle sorting and bedding planes. Bedding planes are generally interpreted by classical stratigraphy as the result of interruptions of sedimentation and hardening of the surface of the last formed layer prior to further sedimentation. The rains having lasted 48 hours and the supply of sediment being continuous throughout the period, it was impossible by simple observation to tell whether the strata had formed successively one on top of the other. In any case, 48 hours gave no time for the surface of a strata to harden before subsequent sediment was deposited on top of it. So the partings had to be explained by some other phenomenon than hardening. This led me to do some experiments on stratification. The first were in France with limited material. From a preliminary investigation of the existing geological and sedimentological data, I was surprised to find that there was no experimental explanation of the formation of strata. It had apparently been assumed that strata form in accordance with the principles of stratigraphy mentioned earlier, but there was no experimental data to confirm the assumption. My first objective was, therefore, to test the assumption by experiment. If it was shown to be correct, then the experiment would have provided the necessary proof. If the assumption was proved to be incorrect, then the tool used by geologists for determining the chronology of fossils and rocks would be shown to be of little value. The second objective would therefore be to provide an experimentally tested mechanism for strata building. I started by examining how sedimentary particles deposited in both dry and wet conditions. In both cases, sand particles of differing size poured into a flask produced microstrata or laminae. The microstrata formed from the particles of sand sorting themselves out according to size, with the larger particles at the bottom grading up to the smaller ones at the top. This fact was fundamental because it showed that microstrata or laminae formed from particle sorting irrespective of the speed of sedimentation, and not, as had been assumed by geologists for 2 centuries, by one layer forming first and then the next one forming on top of it. The results were published by the French Academy of Sciences and decided me to continue my experiments, but on much larger scale. Larger scale experiments required the resources of a laboratory with the latest technology in hydraulics. Having read their reports on sedimentology, I got in touch with the Colorado State University in North America. This contact led to an agreement being signed for a series of experiments to be conducted in their modern hydraulics laboratory at Fort Collins. This is a photo taken outside the laboratory of myself with Piérre Julien and his assistant. Piérre Julien is a lecturer in sedimentology at the university and was in charge of the experiments. They took place in large glass-walled tanks called flumes. Water, laden with sediment, was pumped into a flume, and the way it deposited could be observed and filmed from above and through the sides of the tank. Different-sized particles of sand were poured into water circulating in a flume. The movement of the water caused the particles to be sorted according to their size. Some of the fine and coarse particles were slowed down by either the roughness of the base of the flume or the sediments already deposited. They deposited, causing superposed laminae to form in the direction of the current. A reduction in current caused mainly larger particles to deposit on the previous laminae. Both the finer and coarser particles not contacting the laterally forming stratum continued to be transported by the current. An increase in the current velocity, again due to friction, caused laminae similar to the previous ones to form on top of the stratum of large particles. The accumulation of sediment between two instants of time, T1 and T2, produced a deposit. The deposit consisted of a part of the lower laminae, part of the stratum of large particles, and part of the upper laminae. Each subsequent individual deposit from upstream to downstream was therefore younger than the one before it. If it were possible to differentiate these successive lateral deposits, the time needed for a strata to form could be calculated by adding the difference of time between T1 and T2 to the difference between T2 and T3, and so on. Due to the presence of a current, strata were formed vertically and laterally at the same time in the direction of the current. The experimenter had scope for testing a wide range of conditions by inclining the flume to provide a slope and by regulating the speed of water current and the supply of sediment. As the results of the various experiments were analyzed, it became clear that what had been demonstrated with microstrata in a flask held good on a much larger scale and under all the conditions tested. The flume experiments demonstrated the mechanical nature of stratification, whereby particles segregated according to their size when transported by a current of variable speed. Desiccation or drying out of deposits caused bedding partings. Stratification of the deposit under both dry and water conditions formed parallel to the slope of the initial area of deposit, which could exceed 30 degrees. The results were published by the Geological Society of France. The discovery that strata form sideways and vertically at the same time, strata form in the same way as sequences of facies, the chronology of strata is measured laterally and vertically, provides probably the most important data to emerge from any experiment in sedimentology. The equally important disclosure was the fact earlier mentioned. When the basic principles of geology had been devised, they amazingly had not taken hydraulic conditions into account. Of course, one strata will superpose upon another when sedimentary particles suspended in still water eventually deposit. As soon as the water is disturbed, superposition ceases because the particles are transported in the direction of the current and sorted according to their size. The first major question was to what extent, if any, could these laboratory results confirm the principles of stratigraphy. Continued experiments revealed corroborating evidence that what was taking place was the normal results of sedimentary mechanics. This basic fact had not emerged because of the conviction that sedimentary deposits were time-dependent. The principle of superposition, believed to account for all stages of the geological column, supported the concept of very slow deposition over long periods of time. Experiments on sediment transported by water with varying currents challenged this concept and showed the limited application of the superposition principle. The speed of the water current started at 1 meter per second and gave rise to a deposit of microstrata or laminae prograding downstream. The flow of the current was then reduced to 0.5 meter per second. This provoked the deposit of large particles of sediment. Then, as the deposit thickened, the speed of current was increased back to 1 meter per second, and laminae deposited on the large particles. So the deposit was composed from top to bottom of beds or strata of small particles, large particles, and small particles. The three superposed beds prograded together from upstream to downstream. This demonstrated that the beds or strata did not form one at a time as required by the principle of superposition. They formed simultaneously. Nor did any one bed have the same age at any point as required by the principle of continuity, because they formed together and sideways. Each lateral part of a single bed or strata therefore had a different age. But something else was happening. when the velocity of flow was reduced, a second deposit started forming on top of the first, whilst the first was continuing. The two superposed deposits prograded simultaneously from upstream to downstream. When the velocity of flow was increased, a third deposit started forming on top of the other two, and all three prograded together downstream. Here we have a phenomenon of multiple beds of sediment forming on top of each other, vertically and sideways at the same time, the triggering mechanism having been simple changes of current. The laboratory experiments showed that where there is a water current, one layer does not deposit upon the other, with each layer being older than the one which covers it. This would therefore appear to be a major exception to the principle of superposition. Many parameters were tested, from very slow to very fast currents. None of them, however, provided an example of the principle in operation. The experimental results, therefore, did not confirm the definition that the principle of superposition is a general or inclusive law exemplified in numerous cases. Could it be that the authors of the principle of superposition had not taken hydraulic conditions into account? This possibility would seem to be confirmed by other experiments which showed that the principle of superposition only applied to very fine sediments depositing in water where there is little or no current. The principle applying in such limited conditions can hardly be considered to be a general or inclusive law applying in numerous cases. The fact that stratification formed parallel to the slope, exceeding an angle of 30 degrees, highlights the inaccuracy of the principle of original horizontality, which states that layers or strata form horizontally. It must be remembered that this principle is used by geologists to interpret past conditions producing the sedimentary rock we see today. Sloping strata suggested to them that movement had taken place, causing originally deposited horizontal strata to be tilted at an angle. The experiments show that sloping strata could simply be the result of sediments depositing on an inclined bed. It was shown in the laboratory that the principle of continuity did not apply to strata forming in a current. The strata formed laterally from upstream to downstream in the direction of the current. They did not superpose successively. Consequently, the stratum created in the laboratory did not have the same age at any point as asserted by the principles of stratigraphy. The stratigraphic principles had been used to obtain age correlations between geological formations separated by distances. This fact indicates that no account had been taken of the effect of local currents in the oceans or seas in which the sediments in these geological formations had been deposited. Strata forming in different parts of the same ocean or in different oceans would be subject to differing hydraulic conditions and could not be considered as continuous. The geological column was conceived on the assumption that the principles of stratigraphy applied as a general law with numerous examples. The laboratory demonstration that the principles of stratification do not apply where there is a current challenges the basis upon which the geological column was formed. As with particles of sediment, organisms get swept along laterally by strong currents and deposited successively in sediments in which they become fossils. When the sediments hardened into rock, the position of the fossils provided no indication of age. Fossil 1, in the upper strata, for instance, was deposited before fossil 2 in the lower strata. Fossil 1 could, therefore, be older than fossil 2 in the lower strata. The second major question was to what extent, if any, could these laboratory results explain geological formations around the world. The link between the two was provided by a reference in a 1994 publication entitled Grand Canyon. It contained an item contributed by PhD geologist Stephen Austin, which referred to two papers, one by sedimentologist D.M. Rubin published by Sedimentary Geology, on the relation between hydraulic conditions and stratified structures in the Bay of San Francisco, and the other by J. Southard in Sedimentary Petrology, which summarized 39 series of flume experiments on the same relations. Rubin summarized these relations diagrammatically, showing the speed of current, depth of water, and size of sedimentary particles necessary to produce the different structures found in sedimentary deposits. Having recognized the same structures in sedimentary rocks as those in Rubin's diagram, Austin applied the relationships shown in the diagram to the Tonto Group in the Grand Canyon. This geological formation extends for 800 kilometers from east to west and corresponds to a transgressive sequence of three facies superposed and juxtaposed. The upper facies is limestone, the middle facies clay, and the lower one sandstone. As predicted by Walter's law, the same sequence of facies is found side by side. By means of Rubin's diagram, Austin determined the hydraulic conditions that would have existed when the sediments giving rise to the rock facies of the Tonto Group were deposited. These conditions were principally the velocities of current in the transgression, which caused the water to rise more than 2,000 meters above today's ocean level. The maximum velocity corresponded to the initial erosion of the subjacent rocks by the invading marine waters. The velocity was greater than 2 meters per second. Just a few days, therefore, would have been necessary for the ocean invasion to submerge the entire 800 kilometers. The velocities of currents would have decreased as the transgression reached its peak and before the waters started to subside. It should be noted that the current velocities needed to build the Tonto Group and to transport the sediments correspond to those recorded in the flume experiments. It is therefore not unreasonable to say that strata in the Tonto Group facies would have formed similarly to those in the laboratory, that is to say, vertically and laterally in the direction of the current. As the speed of the current decreased, the particles deposited would have been increasingly fine, giving rise to the three superposed and juxtaposed facies of the Tonto Group of sandstone, clay, and limestone. The advancing water contained differing current velocities. The heavier particles deposit in faster currents than the finer particles. All of the deposits would have taken place virtually simultaneously. The resultant formation of the larger particles of tapied sandstone at the bottom, the lighter bright angel shale or clay in the middle, and the very fine particles of Muev limestone on top is exactly what the flume experiments, Walter's law, and the laws of sedimentary mechanics would predict. There is a perfect correspondence. The deposition of sediment would therefore have been rapid. The coarser particles would have deposited due to the velocity of current falling as the water rose. The finer particles would have started to deposit as the ocean approached its highest point. During the period that the ocean stayed at its maximum level, there would have been little or no current. In the absence of a current, the finest particles would deposit at a speed of about 2 centimeters per day. This is an example where superposition does take place. Being limited to calm water conditions, however, it is excluded as a standard principle of stratigraphy. The deposition of the finer particles would be interrupted by the reappearance of a current when the waters started to subside or regress. During the subsequent marine regression, the reversed currents would have reached velocities sufficient to have eroded deep valleys in the non-consolidated sediments deposited during the transgression. The Tonto Group is attributed to the Cambrian period, which according to the geological timescale, based upon the principle of superposition, lasted 70 million years. The aforementioned data, based upon sedimentary mechanics, would reduce significantly that part of the timescale attributed to the formation of the Tonto Group. Our present research is to evaluate the hydraulic conditions that existed when sediments of present-day geological formations were deposited. As explained, this can be done by examining existing sedimentary rock structures. We need to know more about the velocities of current that transported and deposited the particles of sediment in these structures. In 1935, sedimentologist F. Hjulström observed the movement of sedimentary particles in rivers, and from his measurements he produced a valuable diagram. It shows the correspondence between average velocities of currents and zones of erosion and size, transport and deposit of sedimentary particles. Although the erosion and transport have been carefully measured, the velocities of sedimentation were estimated empirically by Hjulström as 2/3 of the erosion velocities. The object of our new experimental program is to determine these velocities with more precision. The assumptions upon which the formation of rock strata were based had never been verified experimentally. These assumptions, tested by laboratory experiments, are shown to be inapplicable to sediments transported by current. The same experiments showed that strata form according to the laws of mechanics. Our research and experiments demonstrated that the principles of stratigraphy did not apply to stratified deposits formed in the flume experiments when there was a current. Our experiments confirmed and explained on the scale of strata what Johannes Walter had observed on the scale of facies. They showed that the principles of superposition and continuity did not apply in either case. Neither facies nor strata in sequences succeeded each other chronologically. They were deposited simultaneously according to sequence stratigraphy. Rubin and Southard's flume experiments and submarine observations established the relation between hydraulic conditions and structures in deposits. These deposit structures are found in sedimentary rocks. From them, the original hydraulic conditions, and particularly velocity of current, can be determined, as Austin did in the Tonto group. His valuable work is completed by the mechanism of strata formation discovered by our experiments. Superposition and continuity only apply in limited conditions, such as fine sediments in suspension in calm water. In a transgression, regression or progradation, where there is a current, the principles no longer apply. According to the definition, a principle should apply generally. Superposition and continuity should therefore no longer be taught as principles, as they have been proved by experiment not to be a general or inclusive law exemplified in numerous cases. The geological timescale was established on the belief that the principles of stratigraphy applied generally. The empirical proof of their limited application must involve important changes to the scale. The Tonto group was attributed to the Cambrian period, which according to the time scale took 70 million years to form. By application of sedimentary mechanics, it has been shown that the group could have formed within several days or weeks. Our experiments have shown that the principles of stratigraphy are not a general or inclusive law exemplified in numerous cases. They need therefore to be replaced by a method for determining the paleohydraulic conditions that existed when the sedimentary rocks were formed. Data from the past and future referred to earlier will help guide the research.